Hi, and welcome back for the second section of our course on data analysis with Python. This section is about the library NumPy, one of the most important libraries for scientific computing in Python. This video in particular is about creating NumPy arrays. Before we start digging into the details, let's have an overall introduction on the section. Firstly, we'll introduce the library and its more interesting capabilities. The core concept of NumPy is called ND array, which is the data structure for multidimensional arrays. We learn how to perform linear algebra operations with NumPy and how to perform some fundamental operations with NumPy arrays like reshaping, indexing, and slicing. So let's start the discussion on creating NumPy arrays. NumPy is short for numerical Python and is the fundamental package for high-performance scientific computing in Python. It offers one important data structure called ND array to create arrays with n dimensions. This library doesn't offer many particular data analytics features per se, but it's a building block for many other higher-level libraries. So learning about NumPy will allow you to perform more efficient operations when using these higher-level libraries. Installing NumPy should be straightforward when using conda, so the command conda install NumPy should do the trick. Please refer to the installation and setup video if you need more details about how to install Python packages. We start this session by importing the NumPy library. It's common practice to import the library using the alias np. In this way, when we refer to NumPy, we only need to type np. In its simplest form, the creation of a NumPy array takes a list of numbers. You can observe that the type signature for this data structure is NumPy ND array. And of course you can pass a list directly to the array constructor without the extra variable in support. The arrays created so far have just one dimension, so now let's have a look at multidimensional arrays. In this example, we are creating a NumPy array using a list of lists. So here we have two lists, and each of them has 3 elements. This will result in a matrix with 2 rows and 3 columns. We can now observe some information about the matrix. So the matrix has size 6, meaning there are 6 elements. Also the shape of the matrix, 2 rows by 3 columns, is here represented as a tuple with values 2 and 3. The number of dimension of the matrix is 2, and this is given by the attribute ndim. Finally, the specific data type for the elements of this array is given by the attribute dtype. Since we pass a list of 9 integers, NumPy considers the elements of the newly created array as int64, which means integers represented using 64 bits. We could also use the dtype attribute when creating the array in order to force a particular data type for the elements of the new array. In this example, we create a similar array, but we cast it as a float, so the dtype for these elements will be float65. The method sType allows to create a new array by casting the elements of a given array to a given type. So in this example, we create the array y by casting the elements of x as integers. NumPy has many other out-of-the-box functions to create arrays. For example, we can create a matrix populated with zeros. The argument of this function is a tuple to indicate the shape, in this case 3 rows and 2 columns. Similarly, we can create a matrix full of ones, in this case with 2 rows and 3 columns. The I function is useful to generate the identity matrix of a given size. The identity matrix is a squared matrix with ones on the main diagonal and zeros elsewhere. So in this case the matrix is 4 by 4. The diag function is used to create a diagonal matrix. It takes a list of numbers as first argument, and these values will be used to populate the main diagonal of the matrix, while we'll have zeros elsewhere. Next, let's look at a couple of options to generate arrays given a particular range or interval. The first function we consider is the aRange function. It takes the starting point and the end point of a range, and it creates a NumPy array accordingly. So in this example, we have an array of numbers from 0 to 9. Similar to the Python function range, the end value is not included in the array. Also similar to the Python range function, we can specify a third argument, which is the size of the step. In this example, we are generated all the even numbers from 0 to 20, excluding 20. So you can see that the size of the step is 2. A different way to look at intervals is given by the function linspace. This function takes a starting point, an end point, and a number of elements for the array. The output is an array with evenly spread elements. In this case, we have 7 elements spread from 0 to 3. And you can see that the length of the array is what we expect. Next, let's consider repeated lists. In Python, you can multiply a list by a number, and the result is a list whose elements are given by the original list repeated a number of times. So here we have the values 1 and 2 repeated 3 times. We can of course create a NumPy array in a similar fashion. The repeat function does something different. Instead of repeating the list, it repeats the elements of the original list one by one. Next, let's consider stacking. Given 2 matrices, we can create a new one by performing a stacking operation. Vertical stacking, or VStack, assumes that the matrices have the same number of columns. The output is obtained by simply piling the rows of a matrix on top of the other one. So the shape of the output has the same number of columns as the input matrices, while the number of rows is the sum of all the number of rows. So in this case we have 4 rows and 3 columns. Horizontal stacking, or H-stack, assumes that the matrices have the same number of rows. The new matrix has the same number of rows as the input matrices, and these are obtained by joining the elements row by row. The number of columns is the sum of all number of columns, so in this case we have 2 rows and 6 columns. So in summary, in this video we have introduced the library NumPy, one of the main building blocks for scientific computing tools. In particular, we have discussed the core data type for NumPy, which is the multidimensional array, and we have seen a few useful built-in functions to create arrays, including the notion of ranges, repetitions, and stacking.